Then the next protection scheme is the distance relay protection scheme. Here, the distance relay protection scheme simply operates by measuring the impedance of the line. You can either measure impedance, reactance, or admittance of the line. Yeah, let's look at the impedance specifically in this case. Okay, so here is the illustration of how that protection scheme is. So since you need to measure the impedance, you need the voltage transformer and the current transformer, because you know from the Ohm's law as well, you can have the impedance being given as what? The voltage the voltage divided by the current, right? So you utilize the voltage transformer, the current transformer, in order to use that relation to determine the impedance. Okay, so here we consider the radial line here with the bus A, that's probably at one end, and the other bus at the other end, and it has a length specifically denoted here as L, that's the length of the line. Then consider that there is a fault at a point P here within this bus, within this line L, right? That there is a fault. We call it an internal fault at that point P. And we also consider a case where we have an external fault here at a point K. So how will the distance relay protection scheme operate for those various types of fault? Normally, for the external fault that is at that point K, the relay will not operate because the relay will measure the impedance and see that the impedance is greater than the impedance of the line, right? Okay, the impedance greater than the impedance of the line, because the longer the line, the longer the impedance, right? Since the normal impedance of the line has really been set at the level of the relay. So if there is a fault at this other point, the impedance will change, right? Because current will surely, let's say, for example, there's a three-phase short circuit here. Current will not be flowing again in the normal pathway, but it will be flowing through this other pathway. So it will be able to determine the impedance. And so it will be very greater than the normal impedance of the line. And so the relay will not operate for that external fault. Then for an internal fault, we have at the point P, the impedance measured will be less than the impedance of the line, and the relay will operate. Okay. Then we have this relation as well. The impedance at the level of the fault is equal to what we have seen here. Then, with respect to the distances, the fault impedance at that point P can as well be determined with respect to the distance of the fault. That means D divided by the total distance of the line L times the impedance of the line ZL. Right? Okay, so this as well is appropriate to measure or to like determine the location of fault, because you can actually determine it using what this D, right? If you know since you know the total length of the line, and you can measure the fault impedance, right, from the current and voltage transformer reading. So the fault location can as well be predicted, right? Because we know that the fault impedance is directly proportional to the length of the line. Okay, so that's the fault at the primary, right? Of at the primary, or let me say on the line. What is the fault? The sorry, the impedance. The measured impedance, which will be measured at the relay terminals, that will appear the relay terminals, will be what? The current transformation ratio divided by voltage transformation ratio times that fault impedance. So that is the measured fault impedance. Okay, or the measured impedance, sorry, not necessarily fault. Measured impedance. Okay. Then, in order to utilize or to make this relay to operate for fault in one direction, we can add what we call the directional relay. So, adding the directional relay to that distance protection scheme will permit that kind of operation, right? Okay, you can read much more about directional relays. Then we have as well zones of protection in distance relay. For distance relay or distance relaying protection scheme, we can generally zone the network into three different zones: zone 1, zone 2, zone 3. Specifically, they are always specified the range which zone 1 is to be, or zone 2, zone 3. You see it's down. So normally we have the time distance curve as well, right? So for zone 1, the operation of zone 1 should as well be like instantaneous if we have a fault within zone 1, right? So this also has to do with what's like time coordination. For zone 2 here, zone 2 is reacting with respect to what instantaneous time, which zone 1 is supposed to act, plus the coordination time as well. Same thing with zone 3, instantaneous, the time of zone 2 plus this plus what the coordination time. Then how is these zones? How are these zones set? Okay, zone 1 is generally set of 80 to 85% of the line. Zone 2, 120 to 150% of the line. Zone 3, 200 to 250% of the line. So whenever you have a line as such, you can divide it into three protection zones for the uh, distance relay protection scheme. Example, that given a 66 kilovolt radial feeder of 15 kilometers, calculate the zone 1 setting for the distance relay in primary ohms. The line impedance is given as such. So since the line impedance is given as such in ohms per kilometer, right? So you find the line impedance. The line impedance simply will be this impedance per kilometers times the total kilometer length of the line. You know the length has been specified as 15 kilometers. So if you multiply it, you have the total impedance of the line, right? Okay, so that's total impedance of the line primary. Then the zone 1 setting now will be what? We have 0.8 or 80% to 85% of the line impedance. So we utilize 0.8, which is significant of 80% of the impedance of the line. The impedance of the line is it, so we take the magnitude of it to have the magnitude of line impedance, which is the magnitude of 3.6 plus j 1.2, which is the square root of 3.6 squared plus 1.2 squared. You give you that times now 0.8. So this one setting is 10.02 ampere. So that's how you can set it, the distance relay. So same thing here, that we should establish the distance relay protection scheme. We should calculate the zone 1 and zone 2 setting of these relays. So the impedance angle for each line is 75 degrees. The line length is 80 kilometers. The distance relay at bus A is fed by current transformers at 2000 is to rated at 2000 is to 5. Okay, that's ratio times ratio, transformation ratio. Then the voltage transformer rated at uh, this volt, that is 345 kilovolt slash 200 kilovolt star, is to this also a transformation ratio for voltage transformer, is to 120 slash 69 volts star. Okay, so what if you are given this kind to have the transformation ratio? Either you use the primary here and the primary here, or you use the secondary here and the secondary here to calculate its own transformation ratio. Simple. Okay, so zone 1 setting for 85%. Normally, we have 85% of the primary set ohm setting impedance. Okay, the primary impedance of zone 1, uh, 80 ohms, right? Since it falls within this bus A, yeah. So we have 80 from A to B, we have 80 ohms. So we have 0.85, which is 80% times that 80 ohms, which gives us 68 ohm. So that is a primary ohm setting, right? Primary ohm setting. But now that's on the primary. So we need to measure that which will be at the terminal of the relay, which is the measured impedance for that zone 1 setting. We saw the formula up there, which was current transformation ratio divided by voltage transformation ratio times the impedance, the fault impedance. All right. So we have 400 divided by 2,900. It was given, right? Mm, oh, okay, yeah, yeah. So the current transformation ratio here was calculated, which was 200, divided by 5, which gives us 400, and voltage transformation 200,000 divided by 69. As I told you, you either use the primary with this other primary, this other one here, or this with this other one here. Okay, so they utilize 200 kilovolt and the 69 volt here. So that's what it is used to calculate the voltage transformation ratio. So since you have the current transformation ratio and voltage transformation ratio, you have to input it here and multiply. So you have 9.38. That's the zone 1 relay setting. Then for zone 2, we normally said it's from 120 to 150% of the impedance. So we select 140% here. If you still select 120%, it's not wrong. Yeah, we have selected in between 140%. So we have 101.4, which is 140 times what? 80 ohms of that primary ohm setting, right? So it gives us 112. Then we still utilize current transformation ratios, the voltage transformation ratio times that 112 gives us 12 point this. So that's the relay setting of zone 2, right? Simple. Okay, then you can look at exercise 5. Consider the transmission line protection protected by the directional distance relay R1 2 arrow 2 and determine the following: the zones of protection for relay 1 arrow 1 2. So you're just supposed to draw the zones of protection. B, the coordination. That means you have to illustrate the coordination time, right? So this is how you can draw the zones of protection for these, right? Draw the zones: zone 1, zone 2, and zone 3. Then the coordination time, as I told you, uh, if there's a fault here, zone 1, it should react probably as instantaneous time or definite instantaneous time or whatsoever. But now for zone 2, it must be a time delay that is T1 plus coordination time will give us a T2. For T3, it will be T2 plus the coordination time. So you can illustrate that in the figure as this figure is illustrated, right? Then we have example 3 here. Consider 230 kilovolt transmission system shown below. Assume the positive sequence impedance of transmission line. So determine the following: A, maximum load current; B, current transmission ratio. So it's that same. It is the same line. You have to determine these various parameters with zone 1, zone 2, zone 3 setting. I believe I've already seen these, so you can just look at the exercise, how it's solved, and then any uh, questions you can get back to me. Okay. Uh, then okay, this one is a little bit different. So look at this exercise. That given you have this online diagram of this one line diagram of the network of a 138 kilovolt sub transmission line with a line impedance of 0.27 plus J 0.7 per unit. So consider the directional distance relay located at A. Okay, assume that there is a line to line fault at the point F, that there is a fault at this point F, which is located at 0.7 per unit distance. Okay, 0.7, yeah, that's the distance away from bus A. Okay, the magnitude of the fault current is 1.2 per unit as fault current. Assume that the line is the line spacing of Assume that the line spacing of 10.3 feet is equal to the arc length. Okay, uh, the base quantities for power, voltage, and current and impedance are given as 100 megafarad, 138, and so on. Considering only zone 1 and zone 2 protection, determine the following: value of the arc resistance at the fault point in ohms and per unit, value of line impedance including resistance, line impedance, angle without and with arc resistance graphically, whether the relay will clear the fault instantaneously or not. Okay, so for the current, we know that since the current in the arc was given as 1.2 per unit, so the normal current will be what? The 1.2 times, we know we have seen per unit systems. The per unit value of current is equal to what? Actual current divided by the base current. So the actual current will be what? The per unit current times the base current. So we have that 1.2 times that base current, which is 418, which was given in the uh, uh, equation 114, 418 amperes. Sorry, yes, it. So we have the current. So current is 502.8 ampere. So we can calculate the arc resistance from this formula. Okay, so please note this formula where the length there is given in feet. So the arc length here is 8,750 times the length in feet and divided by the current, so the power 1.4. So the length was given specified the distance, the line spacing 10.3 feet. So you just have to input in this equation. Then you have the arc resistance, which is 14.92. Or if you want to put it in per unit, you divide by the actual value. You divide by the base value, sorry. Divide by base value. So which is 190.4. Okay, so per unit value is equal to actual value divided by base value. So you have this actual value divided by that base value, you put it in per unit. Okay, then now the impedance seen by the relay. Normally, the impedance seen by the relay will be the impedance of the line plus the arc resistance. So the impedance of the line was given as we have uh, 0.2 plus J 0.7. 0.2 plus J 0.7, but it was specified that assume that there is a line-to-line fault at the point F, which is located at 0.7 per unit, 0.7 distance away from bus A. So that's the distance, right? So the So the impedance of the line now will be what? 0.7 times that 0.2 plus J 0.7. So that will give us the impedance ZL to that point of that fault. Now plus the arc resistance which we have calculated. So we add the two, you have this. Okay, then see the line impedance angle without the arc resistance. So without the arc resistance angle, normally tan inverse of the imaginary part on real part, right? So the impedance of the line just that fault is what we have this 0.2 times J 0.7 times 0.7, which will give you what? Because we multiply times 0.7 because the line was specified. So we have here 0.14 plus J 0.49. So tan inverse of J 0.49 divided by 0.14 will give us that angle. Then with the arc now, so with the arc that we're going to use now the angle of what? The line plus the impedance of that line due to fault plus the arc, the resistance of the arc, which will give us this. So we'll now use this tan inverse of 0.49 divided by 0.218. So it give us 6.65.98 degrees. So we now use that angle to plot as well the zone characteristic the relay characteristic curve, okay, for the distance relay protection scheme. So that's why we have this angle, this the angles here 6.65.98, which is of the uh, arc, resistance with arc resistance, impedance with arc resistance, and 74 arc without that arc resistance. Okay, so if we want to draw now the zones settings for the zone 1 and zone 2, we'll have something like this for zone 1 and zone 2. Okay, then there's a conclusion. The figure shows that even after addition of arc distance, the fault point F is moved to F prime. You can see that on the diagram here. This fault point here, F here, is moved to this point here, F prime, which is still within zone 1. And so since it's still within zone 1, the fault will be cleared instantly. So that's the conclusion. Okay, then we have